Okay, thank you everyone. And as we're in the sleepy slot before lunch in a dark room with increasing CO2, I'd like to take you back to early Earth, which shares some properties with this, and talk to you about some work I've been doing with an excellent undergraduate student, Victoria MacDonald, who's now to grad school at UW, and my great collaborator, Kelly McCusker. So, we're talking about a problem that I've worked on quite a lot, which is the faint young sun paradox, is main sequence stars get brighter through their lifetime. So for a planet hanging out in the habitable zone like Earth, that means we're going to get a monotonic increase in the solar constant through time. And the geologic record on Earth is well resolved for about the last 3.5 billion years. And it looks like Earth was mostly warmer than it is now. We are in a glacial period now, but evidence of glaciation is largely absent through Earth's history. And in the first 8/9 of Earth history, which we call the Precambrian, there are a few low-latitude glaciations, but largely Earth was ice-free. So we must account for why. So that's the introduction to the problem. A quantity I'm going to use quite a lot is radiative forcing, which to first approximation is proportional to surface temperature change. If we want to go back to a fashionable time period, we need about 50 watts per square meter of radiative forcing. Remember that number, it's going to become important. If we were going to do that with CO2 alone and in a 1D model, so where we took out all the cloud feedbacks, we'd need about 100,000 ppm, and that's not consistent with geochemical forcing. There have been some indications in prior work in 3 dimensions, for example, work by Benjamin Charnay and Eric Wolf, that in 3D, lower CO2 is needed. And what I'm going to do in this talk is really systematically look at the feedbacks involved there. So I want to give you a bit of background first, because no one yet has talked much about evolution of terrestrial planet climates. So this is a cartoon of the evolution of Earth's atmosphere. It has 12 orders of magnitude of dynamic range. So when you're thinking about how might you detect an Earth-like planet, remember that it's really weird and there's a lot of big changes. Some places we can constrain how little we know. Other things where there's an absence of error bars, that implies that I don't even know what the error bars are. And there's lots of stuff back here that in the non-simplified version I might put back in. The gist of this is we're looking at a high CO2 atmosphere. CO2 I've sketched in red here, without oxygen, bit of methane, we're not going to be using that today. That's the kind of atmosphere that we're looking at. And we're going to be looking at clouds. And here is an older paper of mine where I did a parameter space exploration of clouds in 1 dimension. And this is a good plot for looking at what clouds have ever done for us. And short wave, that is reflecting incoming sunlight, and long wave, are the two, that is thermal emission, are the two effects that we would sum to get net thing. So clouds reflect incoming sunlight if the clouds cover a bigger fraction of the sky, if they have more water in them, they reflect more sunlight. So they're more blue, that means they're more of a cooling effect. And it doesn't really matter that much how high we put them. But for the long wave, the thermal effect, it really does matter how high we put them, because low clouds, if we, put a cloud just hovering around the top of my head, we're not going to have a big temperature difference from the surface. So the greenhouse effect comes from a temperature difference. So these low clouds won't have much of a temperature difference. If I got a few tall people, if we stood someone on Dorian's shoulder and put the clouds quite high, they'd be a lot colder than we were down here. So there's going to be a big greenhouse effect from that cloud. So look, this is big red. That means they're going to get a big warming effect. So we sum these together. High clouds, more of them is going to give the warming. Low clouds, more of them is going to give the cooling. So if we want to resolve the faint young sun, we need to take our low clouds. This is how much we have today, and we need to get rid of them. We need to get them down here. This talk, I'm going to be talking mostly about these low clouds and getting rid of them using physics on early Earth. This is an unusual talk for me because no chemistry or biology will be invoked. So here's a photo I took when I was a postdoc at NASA Ames and I was out hiking in Marin counties. This isn't very high. We're looking at low clouds offshore of San Francisco. These are the same clouds in satellites. So these are really good clouds for getting reflection, and they have a lousy greenhouse effect. So visualize this. Visualize a miserable day at AGU when you've just been totally clouded out. So this is the most important slide of the talk, so pay attention. We're going to talk about the physics here. So where do we get low clouds? Typically in the descending limb of the Hadley cell over, it's really good if we've got upwelling cold water. So that's off San Francisco, that's off Peru, off Namibia, that kind of place is really good. So we've got climatological descent here, but a cold sea surface temperature. So we might have warmer air aloft. This is sigma W is a constant wet bulb potential temperature because this is a moist adiabat. And then here we've got a temperature inversion at the top of the atmospheric boundary layer. And we could measure the strength of that inversion with a potential temperature difference, which is called lower tropospheric stability, or a wet bulb potential temperature difference, which is called estimated inversion strength. These are terms from the meteorology literature. So what do we do with our low clouds? Well, convection, shallow convection in the boundary layer is driven by net thermal cooling from the clouds. So these clouds are going to emit black body radiation, they're going to receive back radiation from the atmosphere, and then there's a net cooling. And that net cooling is what drives this shallow circulation here. That's going to help us build the cloud. It's going to bring air up to the point that it can dense here. Now, if we want to get rid of these clouds, we want to entrain dry air from the free troposphere. Remember, this is descending limb of the Hadley cell. So this is nice dry air. And if we entrain this into the boundary layer, that's going to dry out our clouds. So we're back in this, remember, we're in a dark room, not many photons, high CO2. So high CO2 is going to mean that we've got a stronger greenhouse. So this back radiation term here is going to be bigger. So this net radiative cooling is going to be weaker. So that's bad for our clouds. We're not going to form clouds as well. Now, it's become obvious in a slide or two's time, when we've got a weaker solar constant, that's going to be less good at driving convection in the tropics. We've got less sunlight coming in, we'll drive less convection. And it's the moist convection in the tropics which sets the temperature in the whole aloft in the whole atmosphere. So we're going to cool the free troposphere here. So we're going to have a weaker inversion here. That weaker inversion means that we're going to entrain more dry air, and we can dry out those clouds. So low solar constant, high CO2 atmosphere, the hypothesis is that we should have less low clouds. So let's do some model experiments for that. And we're running this with an off-the-shelf version, or in fact, two off-the-shelf versions of the Community Earth System model. We're using a slab ocean, CAM4, 40 years, we'll average the last 20. Everything we're doing modern day, except we're turning solar constant down and turning CO2 up so that we get the same mean surface temperature. Modern continents, modern ozone, modern everything else, because we just want to look at this one feedback and do as controlled an experiment as possible, keeping the model near modern day conditions to as much as we can so that we might actually trust what the model does. There is a hope then. If you want to look at papers where other things have been changed, like rotation rates, continent positions, all that kind of thing that I refer you to papers by Eric Wolf, Benjamin Charnay, who've looked at this kind of problem before. We also did some runs with CAM5 for a smaller range of solar constant. The tendency seems to be the more modern the climate model, the less range of conditions we can run it for. That is progress. So here's the beginning of our model climatology. All these graphs, on the left-hand side, we have our control case. On the right-hand side, so this is the right-hand side of the left-hand plot, that is the middle, we have 0.8 solar constant, and then we have a difference field here. So less solar constant, higher CO2, we have warmer poles, cooler low latitudes. Well, that's because we've got a stronger greenhouse effect. That really matters at the poles, where it's low water vapor. Low solar constant, well, that really matters at the low latitude. This is also good for avoiding glaciation. We have less latent heat flux, not much difference in sensible heat flux. Bit more model climatology. Less CFIT, that goes with less latent heat flux. This is really less vigorous tropical convection. And then these measurements of how strong that inversion at the top of the boundary layer is. The lower tropospheric stability, that is the potential temperature difference. Well, look, we see that is smaller everywhere. We've got a weaker inversion. Then the fancier measure, which is the estimated inversion strength, the difference in wet bulb potential temperature, also just the same thing. That is less everywhere. So we've got this weaker inversion. This is implying to us straight away that we're going to get less low clouds, because these low clouds are just so well correlated to the strength of that inversion. That's in the meteorology literature back to the 1990s, papers from Tony Slingo and others. So this is our climatology looking in slices through the atmosphere. The temperature, we see the same. Potential temperature, we are cooler aloft, as we're expecting. We see that in wet bulb potential temperature here, we're cooler aloft. We're also drier here as well. So now, let's start to look at our clouds. Here we are, low cloud changes. So, white are clouds. There are less clouds. We can even see it without taking a difference field here. So we have annihilated our low clouds here. This is a good result for us. We have completely annihilated them. We've also made them thinner. There's less water in them. And then if we look at this shortwave cloud forcing here, and remember that in a global average sense, we want 50 watts per square meter to resolve the faint young sun. And we've got numbers that are strongly positive, pretty much everywhere here. So we're getting a really kicking shortwave cloud forcing from reducing these low clouds. So this is looking from 110% down to 70% solar forcing. This is a really systematic effect going through. So what we're showing here is that these physical feedbacks on low cloud, which arise from first order changes to the planetary climate, are making a really big contribution to stabilizing planetary climate. Look at high cloud changes just for kicks. Well, what we see is that we do have more high clouds, but they're thinner. So the net effect is quite small. If one was writing a paper on high cloud feedback, one would want to think very carefully about the convection schemes in these models. I'm not writing such a paper, so I'm not thinking that carefully about the convection schemes. And what we see is that really not much happens. It's near net zero here as we go through time. So altogether now, this is looking, as we increase solar constant from the beginning of Earth's history to some billion years in the future, well, this is the gray line here is how much CO2 we'd expect from a 1D model. this is how much CO2 we use. This is less consistent with prior work. And here is the reason here. We have our strong shortwave cloud forcing here. So if we look at the kind of time we're interested in compared to now, the net change in that is about 20 watts per square meter. So out of the 50 we needed, we've got 20 watts per square meter out of this low cloud forcing. As I only have 1 minute and 38 seconds, I will move to my conclusions. Instead of reading you my conclusions, I will say there's some interesting recent work. So I think of a paper by Tapio Schneider in Nature Geoscience this year, actually showing these cloud changes, if you go from a GCM to a large eddy simulation, could be very nonlinear as well. So this is a weakness in this work in GCMs. We show these smooth changes. I might expect to see some even stronger changes than the ones we see, possibly with some nonlinearities involved. But that aside, the take-home message here is that I would like to reclaim for physics 40% of the feedback necessary to resolve stabilizing Earth's climate through Earth's history. Thank you.
A lot of questions. Let's take one at the back first.
Hi, Colin. Very, very interesting. As I discuss in my recent book on the history of planetary climate studies, in the 70s, cloud feedbacks were noted as being the sort of strongest lever available to torque the climate back in the past. There's a very interesting paper in 2001 by Shenwang Wu at Columbia, where he purports to show how the changing balance between low and high cloud could completely stabilize the Earth's feedback throughout geologic time. I mean, it's a 1D model. There's some hand waving, but you're sort of advancing some already well-trodden ground, I think.
Okay, thanks, Al. If you could send me that reference, that'd be great.
Hi, Caitlin Loftus, Harvard. I guess kind of following up in what you were talking about in Tapio's some more kind of resolving cloud models. How much do you expect that we can trust the cloud parameterizations in CAM, given we're looking at such a radically different environment here?
So we use 2 different versions of the community atmosphere model here. And in the different versions, the radiation, boundary layer, and low cloud schemes are all changed. So that gives me, there's not 2 different models, but it's like 1.5 different models. And the general theme of, I think, less low cloud, we've also seen, and Jeremy maybe can comment on this, in the LMDZ model. And I think we've got a good physically based explanation for it. So I'm feeling fairly comfortable at the moment, but always a hierarchy of climate models, and always more climate models would be nice to see.
You mentioned polar amplification. How big's the clear sky shortwave feedback? Does that help you as well?
I have, let's see if it's on here. Is it on here? I have no idea of the answer. I would have to look that up. Yeah. Okay.
One question in the middle.
Could the nonlinearity, if you included it, could it turn on the cloud deck at some point and then cause the first snowball, for example? Like, do you think that's a reasonable hypothesis?
Oh, so let me think about that for a moment. I would be, no, I do not believe it could do that. The reason is that if you decreasing CO2 will help you get low clouds, but then the low clouds respond really quickly. So if you start cooling, well, unless you build low clouds more when you cool, which I don't think you will, then those cloud feedbacks can come off or on quicker than you can glaciate the planet. So that wouldn't be my preferred way of making a snowball. My preferred way of making a snowball is just to bring down CO2.
Gotcha.
Just to follow on from a previous question, another big positive feedback potentially is what happens to the ocean. If you've got a big polar amplification, you're warming the polar regions, part of the inversion is set by these cold waters from cold currents. If the intermediate ocean starts to warm up, you start removing the conditions irrespective of CO2. So if you think about what the ocean is doing with polar amplification, that could make this effect potentially bigger. But you need a couple of GCM to look at it, so that'd be difficult.
Yeah, thanks, Manoj. And we could also do it coupled, or we could potentially do it with just making prescribed making imaginary Q-flux files. And one of my colleagues has been trying to tell me I should do that anyway. So now you're the second person to tell me to do that. Maybe I should listen.
Last question here.
Hey, so Robin Wordsworth, Harvard University. Thanks, Colin. I think this is nice work. How well do you really think we can trust the geochemical proxies?
Well, thanks, Robin. Can we cut off the video feed here? You know, I don't understand the paleosol work, so I won't comment on it. I think Clara Blattler's work with calcium isotopes, where really what it's showing is a DIC to alkalinity ratio, which isn't a CO2 constraint, but is used as one. I think that is probably more that for simple-minded people like me, I can understand that better. So I'm going to quit. Is it lunchtime yet?
So let's thanks again.